Okay, we are in chapter 15 and we are going to go back to kinematics and we're going to see this is a concept from kinematics, which is the direction and velocity and displacement with combined rotation and translation. So remember that we looked at this concept before. There's an origin point where we have a distance a and a distance b. Distance a is origin to a particle a or a point a, and distance b is the origin to a point b. Those distances. R is distance, and it could be in miles, in inches, in meters, whatever. So the concept is just a distance. The distance from A to B is going to be BA. Remember, from vector notation is the head of the vector minus the tail, right? Is the beginning minus, sorry, is the end minus the beginning. However you remember, if you go from A to B by convention in vector notation, from A to B, the distance is B slash A. All right, this is how you read this in any other book. All right, but we saw this before. The distance from, if you cannot measure, or if you want to predict what is the distance of RB, say this is a satellite, this green particle is a satellite, and you want to predict what is the distance in 24 hours. Obviously, you cannot measure it right now because you want to know what is going to be in 24 hours from now. You can predict that distance RB if you know the distance right now and you project the distance that is going to happen in 24 hours, or measure it, whatever you want. Long story short, if you want to know this RB is basically going to be the distance from A to O plus the distance from B to A. All right, we saw this before. All right, so the velocities from B and A at this point are going to be the same, but they don't have to be the same. If they are different, that's when we have the change in R with respect to T, and it gets more complicated. But if the velocity is the same, then it's pretty easy. You just follow this equation. All right, and then you can find the accelerations and the velocities similarly. All right, so let's look at an example, look through these equations as we've talked about this already. In this case, for instance, if the we talked about this too, if the distance is changing with time, then you have something that is omega times the distance. But remember, the omega could be a vector, or actually it is a vector. That's why we have this arrow on top. That means that it's a vector. But if we have a coordinate system, x, y, and z, then this omega is going to have components in I, j, and k, because we're talking about 3 dimensions. All right? Omega then is the cross product of the components and the I, j, k of R. We talked about this in vector notation. So this cross product is going to be basically I, j, k, and then the value of omega and R. Okay, so this is the unit vector, this is omega, and this is R. That's why it's usually simplified to an angular velocity, where you just know the magnitude and take the component in the k direction, k with z direction. This is also expressed as omega dot, because remember the omega is also expressed as theta dot, because theta is the angle between the original point and the later point. Okay, you can see from the image omega is, I'm talking about theta, I'm sorry, theta right here. Theta is this angle between the point, the location of the point with respect to its original distance. All right, so let's talk about omega for a minute here. What is the direction and velocity of point A on the turbine? So I noticed that sometimes this concept could be hard to understand, but it's actually pretty simple. Maybe that's why sometimes it's complicated, because it's so simple that you might think that is not correct. But omega is the magnitude. Okay, so say 10 RPMs, revolutions per minute, or could be in radians per second. Okay, and the way to convert these two is through a 2 pi multiplication, 2 times pi. Okay, but that is just the magnitude of something rotating. If you want to know the velocity of a point with respect to the origin, then you need the distance. And as you notice, if you multiply something times that constant, then the value is going to be different. So they're asking us what the direction and velocity of point A of the turbine blade is. So if this is origin, then you have to specify if this is your negative or your positive direction. If you choose negative, then you have to multiply minus distance times the value of omega. Okay, and then you also have to know if your clockwise or counterclockwise is positive or negative. So if, say, for example, A was your origin and this point is positive, but it's counterclockwise, which is also positive, then the value is negative. But if your origin is at the beginning of the blade of the turbine, which usually that's the case, because it's when you have your R or your origin, and then everything else is the radius or to create your circle, right? You follow? So at this point it's positive, but when you specify the velocity, velocity has magnitude and direction. So in this point right here is going to be a negative distance. All right, as long as you follow that, you understand the whole concept. Obviously at this point it will be a positive distance. So it's going to be, what is the direction of the turbine? So it's going to be positive by the counterclockwise, and then negative by the distance from origin to A. All right. So this is saying that that direction at point A is going to be downwards. All right. And it's very easy to see. If you follow the omega cross K or R, that you will notice that that value is going to give you that the tangential velocity at this point is going downward. So when you pass through this point, you'll be going that direction. If you want to know that this point is going to be that direction, and if you want to know that this point is going to be that direction, and at this point is going to be that direction, etc., until you form these vectorial tangents. Remember that in this circular path, the vectors are tangent to the direction. Okay. All right. And this is basically what we're saying. So the length is in the velocity is going to be omega cross L. All right, or omega cross R better. Well, in this case, R is L. And you can tell that it's negative going downwards because this is negative I, right? It's going to the left. And omega always has, if you have X and Y, omega is going to be in the K direction because this is a rotation. All right, we talked about this already, so this shouldn't be a surprise. If you still have issues with the concept, you need to contact me. All right, so we also talked about this, so I'm sorry to keep delaying the examples. So the V dt, velocity with respect to time. If you have a rotational system, it's going to be omega cross r. So you apply the chain rule, or in this case is linear combination because each variable has a component in time. So it's omega with respect to r and omega with respect to the derivative of r and dt, right? So omega with respect to t, r with respect to t, but this is a calculus rule, so you probably recognize this rule. If you divide, well, I don't want to confuse you, but it's positive because you're multiplying. And similarly with the acceleration. So let me go ahead and jump to the example. These examples are straightforward. There's one good okay, this one is a good one. Let me see if there's another one. We'll do this one later. Let's do this one right here. So we have a system that is fixed at A. So if you want, A would be kind of like the origin in our conversation. And we have a piston that is moving in a linear fashion. Okay, so this only goes left and right, maybe like pushing something or creating combustion, whatever it is. Maybe this is pushing the piston, or it could be that there's like an engine combustion right here. That's what is pushing the engine. Whatever it is, remember, we don't care about the story. We care about what happens at point 1 and point B. And what they're telling us is they are telling us that crank AB, so this element, has a constant clockwise. Okay, so clockwise is this direction. Angular velocity of 2,000 revolutions per minute. Okay. Now, for the position indicated, determine A, the angular velocity of the rod, B, and D. Okay, so the angular velocity of this element and the velocity of piston P. All right, cool. So this has a rotational and translational component. So we're going to have to find translational plus rotational component. All right, so maybe the rotational component would be something like that. And then we'll have to add the rotational component of the velocity. And that will be the total velocity. This right here, you'll see it a lot. It's called a linear combination. So this is a very simple system, even though it looks complicated. You can have a non-linear combination, which is that both of them are multiplied, or kind of in fluid dynamics actually, you have convection effects where they are not linear combination. The convection effect is a non-linear combination because it has a translational, a rotational, plus the combination of both those two. So they have that summation plus the multiplication, but don't worry about that right now. Right now is, believe it or not, is going to be the simplest case where you only add the translational and rotational components. All right, so let's start by looking at what we have to do. We have to follow this equation for accelerations, for displacements, for everything is the translational component plus the rotational component. So as long as we get to this point, we can find anything we want. This part, D to B, will be the rotational, and this will be, sorry, this will be the rotational, and this will be the translational. Okay. All right. So let's go ahead and let's solve it. So from this point right here, remember that we have, first of all, this is given. This is 2000 RPM. The dimensions are given, 3 inches, and this 40 degrees was given. So if we choose the rotational, the clockwise direction will be this guy right here. Obviously it's omega, but the tangential component, remember that's why we did the turbine example or the turbine question. this is the tangent. This is the velocity vector at that point. So if you take a triangular element or a triangle where this is 40 and this is 90, then this is 50. Therefore, if you put a horizontal line here, this will be 50, which is this case. So we have this angle at 50. Okay, that will take us a long way because it's the angle that we're going to use cosine of for velocity at point B. So the first thing is, remember, we talked about this before, the revolutions per minute, take it to radians per second. It's very simple. 1 minute has 60 seconds, and 1 revolution is 2 pi radians. So if you multiply 2,000 times 2 times pi divided by 60, you're going to get 2.904, or you can even round it to 210 radians per second. Right? So if you have, what this means is if you have a circle of perimeter 2 pi, you're going around that circle, running around that circle 209.4 times per second. So a lot of energy to do that. So this system has quite a lot of energy. It's doing, or you can even see it in 1 minute, in 60 seconds, you're taking this this mechanism and rotating it 2,000 times. All right, this is radians per second. And now, if you remember, this is again going to the turbine example, that radians per second, which is omega, in the clockwise direction, times the distance, 3 inches, is going to be, this is r, times omega, is 3 times 209.4 is, careful here, this is inches. We probably have to take it either to meters or feet. So we'll see what the example tells us to do. It's telling us that, it's not computed. We'll have to go to a calculator and do this. But if it's 210, will be 210 times 3 will be 420, 630. So it's going to be approximately 630 radians per second times inches. So inches per second. 630 inches per second is the tangential velocity. Okay, so VB, this is approximately 630 inches per second. Maybe check if we need to take this into feet. We'll check that in a minute. All right, the second part is that since this is 50 and this is 40, we should be able to find this pretty easy. So if you form a triangle with that distance, well, or with the angle right here, 40 and 3 and 18, 18 inches. And 40, we can find this beta angle by doing sine of sine rule. So we know that this angle with that side and this angle with that side, or that angle with that side, but we really don't need this angle for anything because we only have this angle 40, so we can use 40 to 18 and 3 to beta. So it's right here, sine of 40 divided by 8, right? So the angle, oh, it's not 18, sorry, it's 8. Say 18, I apologize. So sine of 40 with respect to 8 is equal to sine of beta with respect to 3. That's what we have here. Yeah, very simple to solve. 3 divided by 8 times sine 40, and this is in degrees. Even though this is in radians, we're going to find the angles in degrees. So don't get confused. Radians is only for the angular velocity. Everything else in the geometry of it is going to be in degrees. So beta, finding the sine of this is a number, sine of 40 degrees is a number, times 3 divided by 8, and then sine inverse of that. So this is sine inverse of beta equals sine inverse of 3 divided by 8 times sine of 40. If you take that into calculator, you're going to get about 14 degrees, 13.95. All right, so we have beta and we have the distance 3 and 8. If you needed to, you can actually use sine again, sine rule, and find this one, but it seems like we won't need to find it. Yeah, we won't, because at this point, we can do the translational and rotational velocity. Okay, so translation is the velocity at v, so the tangent, and rotation is because this component of the 2b. So in my equation, I said something that is not true. This is the rotational component, and this is the translational component. B velocity at b is translational, and this d to b is the rotational. Okay, so what we need to do is basically do that combination. Okay, so if you notice, this is just going to be a pretty straightforward concept. So we have the velocity at bv that we found, which is 610 or something close to that. Yeah, 628.3, and that is our velocity at point B. All right, the velocity at point D is delta, which is the one we want to find. Remember, velocity at point D as delta is equal to velocity at B as boy plus the velocity from D to B. Okay, so the one that we want to find, okay, this is going to be the longer side of the triangle, and then the rotational velocity closing the triangle is D to B. Okay, so let's see what we have. We have the angles. So since we're using the horizontal one, we found that up here, the horizontal angle is 50, and the horizontal angle is going to be the difference. Let's see, this is the horizontal with respect to, we cannot use 13.95 because this right here, this angle 13.95 is the angle from B to D. If you notice, from B to D, and that angle with respect to a horizontal plane is beta. What we need is this angle right here. We need this angle, which is what is moving at point B. This angle right here is going to be 90 minus 13.95 degrees minus beta, basically. 90 minus beta. And 90 minus beta is 76.05. Okay, so this is 76.05. You can see it, right? You have 50 right here, and you have this angle right here, which is 76.05. Okay, and then you have one of these velocities, what is the one we found, which is velocity at B, which is 3 inches times 209 radians per second, and that is 630, let's say 628.3 inches per second. So it's again line, there's going to be a rule of sines. So sine of 50 with respect to velocity from D to B. So velocity from D to B over sine of 50 is equal to, we have to find this one, so we have to use a known value, velocity at point B as boy, and sine of 76.05. All right, multiplying this and doing sine inverse, we find velocity of b. And you can do rule of sines again to find the velocity at d, which we don't know what is the velocity, the linear velocity of d, which is actually what they ask. So in a way, we don't even need to find this if we don't want. What they're asking us to find is velocity at d. Velocity at d, this guy, velocity at d, over, so this angle is going to be 180 minus 50 minus 76.05, and that is 53.95. So velocity at d over sine of 53.95 degrees is equal to, you can use velocity at b, which is 628.3 divided sine of 76.05. All right, solving for that, we should be able to find it. Okay, velocity at d is 523.4 inches or 43.6 feet per second. So this element is going at 43 feet per second. It's pretty fast. It's going left and right. It's going, well, at this point, is going at 43 feet per second, which if that is a constant 2000 RPM, that will be going right and left, right and left and right, left and right at a constant of 43.6 feet per second. All right, so this is how you solve this type of problems where you have rotational and translational forces. If, let me get rid of all this, we have one last concept. Okay, now if you wanted to find, what is the second question, question B? Yeah, the velocity of the piston P, that is actually the velocity at D, but the first question is the angular velocity at rod BD. Okay, for that point, the angular velocity is going to be the length times omega BD is equal to the velocity from D to B. So we have this, which is 43.6 feet per second. And if we divide by the length, which is 8 inches, we get 63 radians per second. So look how interesting. It goes from, let's see. All right, this bar is going around 210 radians per second, and is doing all that movement, and this line, or this bar, B to D, is going extending, going back, extending, going back, and since the length is much longer, the velocity is less, and that is only happening at, what was the value? 62 radians per second. So it's reduced to 62 radians per second. So look how interesting. This is going at 210 radians per second, the bar AB, but the bar BD is only going at 62 radians per second, almost 4 times less.